Hi, welcome to our fifth Physics Advanced Higher Hangout for tonight. We're going to spend another 20 or 25 minutes revising some of the questions which will probably come up in the Advanced Higher Physics paper, which is just a few weeks off, May the 5th being the day of the exam. But we've got plenty of time to finish our reports, and we've also got time to do our revision as well. So without further ado, we'll now turn to our screen share and start our revision for tonight. And there we go. I told you not to miss Mr. Mallon's Advanced Higher Hangout as a wee starter for certain members of our class which don't tune in, but I'm sure you'll tune in this time. I'm sure you'll tune into it on the YouTube channel. So we begin with the Advanced Higher Division Hangout for tonight. Albert Einstein looking very happy indeed because he knows that the course is finished and it's just revision to do. So I hope you get a lot of benefit out of this revision tonight, and we'll start off with our first question. And here it is here. The first question is to do with electric current in a wire. Let's see what the question is all about. And it's asking us then, find the magnetic induction B at a distance 20 centimeters from the wire if it's carrying a current of 0.5 amps. So here we have the electric wire here, and the current is moving up it, and I'm drawing in the lines of the magnetic induction field. Let's have a quick sort of like a revision of how we find the direction of the magnetic field lines. And we can use our left hand rule, and I can trust that you can use your left hand rule on the screen at the moment. Your thumb is in the direction of the electric current, which is up the way. And if you curl your hand round, where your fingers are pointing will be the direction of the electric field. So in this particular case then, sorry, the magnetic field will be pointing like that direction, and pointing that direction there, that direction there, and that direction there. Just check by your hand going round there. Now, what is the expression for the magnetic induction B a certain distance away from the wire? Well, that's this equation here. The magnetic induction B equals mu naught, which is just a constant, divided by 2 pi times the current, which is going to be in the wire, divided by R. So all we really have to do is to plug these values into the equation to get the magnetic induction field at a distance from the center of this wire. In this particular case, it's 20 centimeters. So let's plug in our numbers then. We start off with the equation. The magnetic field, or the magnetic induction B, is mu naught times the current I divided by 2 pi times the distance R away from the center of the wire. Now, mu naught is given the following value. It's 4 pi times 10 to the minus 7. It will be in the data book, Tesla meters per amp. What a kind of a unit that is, but that's the constant, and it'll be in the data book. And all we have to do is plug into the equation. So we do as follows. So we have 4 pi times 10 to the minus 7 times the current flowing in the wire, and the current flowing in the wire is 0.5 amps, so that's quite easy to do, 0.5 amps. And we divide that by 2 pi, which I'm just leaving the moment is 2 pi, times the radius, which is 20 centimeters, times 20 times 10 to the minus 2 of a meter. Now, if we do our calculation, we should end up with the B field equal to 5 times 10 to the minus 7 Tesla. Remember, T stands for Tesla. And that's the first little equation, our first little question done for tonight. Key points here. The magnetic field round the wire can be found with the left-hand grasp rule. Thumb is the electron flow, and the fingers curl round to show the direction of the magnetic field. So in this case, it's coming out of the page here and into the page, out of the page and into the page. And the magnetic field forms concentric circles round the wire. And because it's proportional to 1 upon the radius, then of course the further you get out, the magnetic induction B field will decrease. So, good wee question. Take a wee minute to look at it when you're replaying the video, and that's the key question, the key equation up here, which will be in your data book. The magnetic induction for round a current carrying wire. Now that brings us on to our second revision question for tonight, still based on this idea here. And it's to calculate the force between two parallel conductors. Now, we've already done this one here using the left-hand grasp rule that it is there. We can see that the magnetic field will curl round the wire like this. So in this particular diagram, we can see it's in the right direction. So if we go a certain distance away from this wire, we have an expression for the magnetic field. So in this case, the magnetic field will be stretching well out here and starting to influence this other conductor, which the current is going to be moving up as well. Now, at a distance r away from the first conductor, the magnetic field B is given by a previous question. Mu naught I, in this case, is going to be I1, divided by 2 pi r, r being the distance away. And it's this magnetic field induction, the magnetic induction field B here, which is going to influence this conductor here. Now, if there's a current flowing in this conductor, it will be affected by the magnetic field of this conductor. Now, if I can draw this symbol here, this shows you the magnetic field at this particular point due to conductor 1 is coming out of the page. Now, I'll leave you to do the right hand rule because we know the force experienced by that conductor. The force is going to equal to the current flowing in it, which is I2, times the length of the conductor, times the magnetic B induction field due to this conductor 1 here, and times sine of the angle in between the B field and the current. In this particular case, the current is moving up the way and the B field is coming out the way. So therefore, the perpendicular sine theta is going to be sine 90, which is 1. And therefore, the force experienced by the second conductor is going to equal to the current flowing in it times the length times the magnetic B field due to the first conductor. But we know that already. We know that this expression here is the magnetic B field due to the first conductor. So all we have to do really is just swap that B with this B here. So we have the force acting on the second conductor is going to equal to I2 times L times mu naught I1, current in the first conductor, divided by 2 pi times the distance the two conductors are apart, and that is r here. Now we can tidy this up a wee bit by saying that the force per unit length of the conductor, which is more of the question I'll ask you, the force per unit length of the conductor is going to equal to I1, I2, divided by, I've got the mu naught as well, I1, I2 times mu naught divided by 2 pi r. So there is the expression for the force per unit length of a conductor carrying a current in the presence of another conductor carrying the current. And they will ask you that in the advanced hat. It's a well-known kind of proof to ask. So you can see that if you do the right hand rule, field pointing out of the screen, current moving up the way, there'll be a force acting on that conductor in such a way that it will be pull the conductor together like that. So the two conductors will be attracted together like that. I'll leave you to do the other situation where we have the current moving up the way in this conductor and the current moving down in this conductor. And as we saw in the lab, the two wires push apart. So there we have the force between two parallel conductors is given by this final little equation here, and you have to really learn that and learn the proof of it as it's done there. Okay, 2 questions done in our revision for tonight, our hangout. Let's move to another topic and see what's behind the arrow. Oh, what is this one? Let's take a little minute to read this. First of all, we have a Ferris wheel going round. like the one in Glasgow Green during the Commonwealth Games, or the one in Strathclyde Park. Find the rotational kinetic energy of the Ferris wheel. Now, what we got then? We are given the moment of inertia of the empty wheel is that kilogram meter squared. We're told that the maximum passenger mass per chair is that. Oh, we're told the number of chairs is 20, and you can count them and see later on. And we're told that the radius of the wheel from here out to here has got to be 10 meters. So the radius of the wheel is 10 meters. And the period of rotation has got to be 60 seconds. So from that information, we have to try and work out the rotational kinetic energy of the wheel. Now, what is the rotational kinetic energy of any object that's moving? We can write down from the data book, the rotational kinetic energy is equal to 1/2 times the moment of inertia of the system times omega squared. So that's what we have to go on. And from that, we have to find the energy of rotation, the kinetic energy of rotation. Well, right away from the period of rotation, 60 seconds, I can work out omega, the angular velocity. How can I do that? Well, omega, we know, is equal to 2 pi f, always. And we also know that the frequency is equal to 1 upon the period. So we have 2 pi divided by the period of rotation. So I can go right away and say, well, omega must be equal to 2 pi over 60 seconds. So we have that. So omega then is equal to pi divided by 30, and the units for the radians per second. So we have got the first part of the information, omega. Omega is equal to pi upon 30 radians per second, found from that little formula at the top there. So that's no any problems. Now, what's next then? We have to find the moment of inertia of the system. Now, telling you the moment of inertia of the empty wheel is this value here, 9.5 times 10 to the power 5 kilograms per meter squared. But we have to know the moment of inertia of the 20 system. 20 kind of like particles, if you can imagine it, stretched out along the circumference of this circle. Now, we know that the moment of inertia for a mass at the end of a circumference, we'll just call I, is going to equal to mr squared. M being the particular mass of the particle and r being the radius from the center. Now, because there are 20 of them, then we need to write down I is got to equal to 20 times the mass of one of these little cabins, and one cabin chair is going to be 200 kilograms maximum, so we can find 200 times that. So it's 20 times 200 times the radius it is away squared. 10 tens are 100. So right away we can work out then the moment of inertia of the system due to all the cabins and all the passenger chairs. So 20 times 200 times 100 times 100 is going to give you 400,000, and the units for the moment of inertia is kilograms meter squared. But that's not the total inertia, total moment of inertia of the system. We have to add in the empty one as well, which is up here. So we can write down in black here the total moment of inertia is going to be 400,000. That's due to all the chairs plus 9.5 times 10 to the power 5. And remember, it's all in kilograms meter squared. So the total moment of inertia becomes equal to 1.35, you do the calculation, times 10 to the power 6 kilogram meter squared. So all we have to do is use our kinetic, our rotational energy equation. So the energy of rotation we know is equal to 1/2 times the total now moment of inertia times omega squared. We just plug in the numbers. It's quite easy to do after this now. 1/2 times 1.35 times 10 to the power 6 times omega squared. I'm just going to say pi squared divided by 3^9,900. And if you take your time and do the calculation, you should have 7,000, about 402 joules. So that's the rotation energy of that Ferris wheel, which is quite an accurate figure of it. So good question to do. What are the pitfalls for it? The pitfalls for it are just focusing into the moment inertia of the empty wheel and doing the equation here, and forget that you have to add up all the moment of inertias of these cabins, which are acting like particles at the end of a circle, and that's the moment inertia is given by mr squared for that one. That's that equation here. So that's what you've got to remember. After that, it should be quite easy. One of the hardest things people find is working out the angular velocity just by giving the period of rotation, and that's this part here, which has to be learned. Omega equals 2 pi f equals 2 pi upon the period, 2 pi upon 60, and units are radians per second. So good question to revise, and be ready for questions like that, because questions like that will in fact turn up where you maybe have to add on moments of inertia. Okay, let's move on to our next revision question. Remember, the video is recorded on the YouTube channel. You can go back and you can watch the steps of the calculation and do the calculation as it happens. So you've got plenty of opportunity to go back if you miss out a step live. Next question coming up, and it's the skater. We haven't done this for a while, so let's see what the question is. It's, why does a skater spin faster when she pulls in her arms? Remember, we did that in the rotating chair, or sorry, rotating platform in the classroom, which made me very dizzy. But why do they get faster? Why is that? Well, the answer to that is it's all got to do with the angular momentum, which is the equivalent of the linear momentum. It works the same principle, because just as linear momentum is conserved, then the angular momentum is conserved as well. So the reason why she spins faster is due to the fact that you need to have conservation of angular momentum. So this skater here, when she throws her arms out quite wide, remember our last equation there, we had mr squared for the particle in a circle. The moment of inertia was mr squared. Well, what this tells us is that the bigger the distance of your arms, or you throw your arms out the way, you're putting the mass further out. So as you put the mass further out, you're creating a high angular, you're creating a high moment of inertia. So you're going to get a high moment of inertia, which we'll call I1. So you might be spinning round here with a certain angular velocity, which we'll call omega 1. And because your arms are full out the way, you're going to have a high moment of inertia. Bring your arms in closer, and you're going to decrease your moment of inertia. You're going to then have a low moment of inertia. Now, because it's conservation of angular momentum, we can write down this equation here. We can say I1 omega 1 must be the same as I2 omega 2. Now, if you have put down a low, if your second moment of inertia is low, then it means in order to keep the conservation equation correct, you must have a faster angle of rotation. And that's really why the skater speeds up, is to keep the conservation of angular momentum. So that's a good wee story that. It can be learned. And it's also applicable to astronomy, because we have stars which collapse in on themselves. Stars collapse, and a large star which is having a certain omega collapses in itself to a smaller star. We find out that the angular velocity actually increases to a larger angular velocity, that is, the spin becomes faster. And it's all due to this very important detail here called the conservation of angular momentum. So that can explain how skaters go faster, how divers go faster when they sort of like curl in together, and even astronomy, where we have stars collapsing. It means they will in fact rotate faster. So it's a fascinating topic, that. It's all down to conservation of angular momentum. Okay, what's our next question for this evening? Oh, right, what's this one? It's to do with the electric field around a charged conductor. Now, there's the equation for the electric field. Remember, the electric field is the force experienced by a unit positive charge when it's in the presence of a large charge Q. So what we have here is the electric field is 1 upon 4 pi epsilon naught Q over R squared. Now, for a charged conductor, all the charge resides on the surface of the conductor. There is no charge inside the conductor. So basically, there's no field lines inside the conductor. All the field lines emanate from actually the surface. So all the field lines emanate from round here. I'll just draw in a few just to show you now. In fact, it goes all the way around in a radial circle. And it appears that the field lines emanate from the centre. Now, because there's no field lines inside the charged conductor, because all the charges reside on the outside, then there can be no electric field in the conductor. So really, what we have here, if we draw the graph, and we draw a thicker pen for you here, if we draw the graph of this, then there's no electric field inside the conductor. At the surface of the conductor, the electric field strength is given by Q over A squared, where A is being the radius from the centre out to here. So at the surface of the conductor, the electric field at the surface is going to be Q over 4 pi epsilon naught A squared. Now, after that, we have the 1 upon R squared drop off. So it does that. So the electric field strength drops off in proportional to R squared. So the electric field strength follows the inverse square law from the surface of the sphere all the way down. Remember, it's symmetrical, so the other side of the sphere does the same. It will tail off 1 upon R squared as well. And remember, the electric field strength at the surface of the sphere is Q over 4 pi epsilon naught A squared. So the electric field around a charged conductor, at the surface, Q over 4 pi epsilon naught A squared, and outside the surface, it tails off 1 upon R squared. Inside the conductor, there are no electric field lines, so if you draw a circle around anywhere inside the conductor, there'll be no lines cutting that circle. So there's no electric field inside a charged conductor. And remember, you can look up your notes to look up the idea of shielding, which we use in computer wires, any wires that carry data, or even we can have shielding in cars where we can't, in fact, receive radio signals because there's no electric field inside a charged conductor. So a graph to remember and a fact to remember: inside a charged conductor, no electric field. Now, I know what you're going to ask next. What about the electric potential around a charged conductor? Well, the electric potential around a charged conductor is given by the formula Q over 4 pi epsilon naught R. Remember what that means? That means the work done on a unit positive charge, taking it from infinity to a certain point near the surface. So at the surface of the charged conductor, the electric potential V will be equal to simply Q, the charge residing on the conductor surface, divided by 4 pi epsilon naught A, where A is the radius of it. But here comes the interesting fact. Because there's no electric field in the charged conductor, there'll be no electric field lines. So if I take a charge and move it from the surface into the sphere to any particular point, I'll not be going across any electric field lines. And if I'm not going across any electric field lines, I'm not doing work. And if I'm not doing work, I'm not adding to the potential. So really, inside the sphere, the electric potential will be exactly the same as the potential at the surface. Outside the sphere, it will fall off 1 upon r. Now that's a very important argument to rehearse. The electric potential inside the charged sphere is exactly the same as the electric potential at the surface of the charged sphere. The reason being, inside the charged conductor, there is no electric field lines. So if I want to move a particular charge from here and move it anywhere in here, I am not going to be crossing or moving against or moving with any electric field lines. Therefore, I'm not going to be doing work on the charge, and therefore there is no work being added to the charge. Therefore, there's going to be no increase in its potential. So the potential remains constant inside the charged conductor. So these are two graphs you have to know and know very well. We did the previous one there. The electric field inside the charged conductor is 0, and it falls off 1 upon r squared outside the sphere. But for a electric potential around a charged conductor, it's the same inside anywhere in the sphere, same value as at the surface, q over 4 pi epsilon naught a. So anywhere in the surface here, it'll be q over 4 pi epsilon naught a. And outside, the potential varies with 1 upon r, which is different from 1 upon r squared. So remember that on those two graphs, electric field and electric potential, and no doubt about it, you have a good understanding of charged spheres, charged conductors. Okay, nearly there for our hangouts. So what's the next question waiting in the wings? Let's see. Oh, right, it's called this one. It's explain the difference between unpolarized light and plain polarized light. We did this a few days ago in the class, and here's a quick picture to help you remember. We know that unpolarized waves, the electric component and the magnetic component, are vibrating in different planes. There's one particular plane here, and there's another particular plane there, another one there, another one there. So really we can draw billions of these in, but for the sake of simplicity, we'll just join 1, 2, 3, 4, 4 planes there. So unpolarized light, the electric field component and the magnetic field component are vibrating up and down, along that way, and along that way, and along that way. So what's polarized light? Polarized light is light which is vibrating in one plane only. It's vibrating in this one plane here. The polarizer is some sort of film made up of molecules, long chain molecules, which actually absorb the components of the electric field. Now, I know I've drawn a diagram there showing you the transmission axis being vertical, but that's really not what happens. But for the sake of advanced higher, we'll run with it. We'll try and run with the idea of the broomsticks going towards the railing, and only the broomstick, which is vertical, gets through. Now, we know that's not the truth. We know that when we slightly turn the polarizer, another polarizer behind here, we still get transmission of light, which follows Malice's law. Now, that's because it's only the component of the plane which gets through as well. So in strict physics language, the line should be across that way, because what happens is it's this component here which is absorbed by the molecules in this direction. Therefore, it takes that out, and it just leaves the vertical one to come through. But we're not getting into any big detail. We'll just think for a moment of the rays and the broom handles for our description of polarized and unpolarized light. Okay. Our final little question for tonight is this one here. It's a tank of water, and we've all seen this before looking at lochs and rivers, especially when the sunshine is out. What we get is quite a lot of glare if we look towards the surface of the lake, and that's because the light is reflected off the surface of the lake. And that can be quite annoying if you're a fisherman, or you're sailing a ship, or even if you're driving in the road and the road has got some water on it and the sun comes out and the glare off the road is quite perturbing for the eye. It can be quite distracting. So in this particular case here, we have what we call, we can get rid of that by putting in front of our eyes a polarized lens. And the polarized lens in front of the eye will reduce the glare. Why does it do that? It does that because when light from the sun comes in, it will be unpolarized. But when it reflects off the surface, or the surface of any non-conducting material, it will be partially plain polarized. So you'll get light vibrating in one direction. So if you have got some sunglasses on which the lines of transmission are that way, you'll block out a good bit of that reflection. The refracted ray is also kind of slightly polarized as well, and there's a certain angle which is related to the refractive index. It's called the Brewster angle, and at that particular angle, the reflection of it where can be controlled by blocking it with the polarizer, and it works for a certain angle. Now, the Brewster equation is this one here. The refractive index is tan IP. Now, how do we get that? How do we get that from here? Well, when the light comes in and reflects, it will have the same angle IP. Remember, IP is what we call the Brewster angle, and that's the angle where viewed with a polarizer, we're going to have, we can reduce the glare, because at that particular angle the light will be maximized polarized. So how do we get this expression here, n equals tan IP? Well, we can just do it with Snell's law, and Snell's law is just simply sine incidence, which we'll call IP, divided by sine of the refracted angle, and that's equal to the refractive index. But we could do some work here, because the Brewster angle is such that the angle between the deflected ray and the refracted ray is 90 degrees. That's the key point here. So we can express angle R in terms of IP. If we just go to the side of a page and say, well, that's the full 180 degrees, we can say that 180 degrees is going to equal angle R plus 90 plus IP. So that would imply then, if we do a wee bit rearranging, the refracted angle between the normal R is going to be equal to 180, take away 90, take away the Brewster angle IP. So R equals 90, take away IP. So we can put that into Snell's law, and that will be equal to sine IP divided by sine of R, which is going to be 90, take away IP. And if you remember your trig relationships, sine 90 minus IP, or sine 90 minus an angle, we can rewrite it as cos of that angle. So we have sine IP over cos of IP, and that equals the refractive index. And we know that sine over cos is tan, so that would imply that tan of this Brewster angle IP is equal to the refractive index. So in this particular case, the refractive index of the material is 1.52. So if you plug that into your equation here, we'll do this in red for you, we find out that the Brewster angle IP, and you can work this out for yourself, is about equal to about 30. The Brewster angle is about 56.7 degrees. So that's the angle which would be reflected, which would give you the near enough plane polarized light, which can be reduced by the polarized lens in front of the eye. The glare would be reduced. Now, that's ended our little bit of hangout for tonight. We'll run over the half-hour mark, but I hope you've enjoyed it. I hope you've enjoyed the different parts of it. And I'll go back to the big screen again. I think it's here. Oh, sorry. Oh. Go back to the the big screen. I thought it was on the other one there, sorry, so stop sharing. And go back to the, hopefully we'll get another hangout before the Easter holidays. I think I'm don't know whether I'm sharing this or not right now. I need to go back and check. Oh yeah, I'm here. Sorry, you get that Google look when you're looking about your computer screen trying to find out whether you're on live or not. I now see the live button up there. So I hope you enjoyed this hangout for tonight then. I hope you have watched it. You can catch it up on the YouTube channel, and I plan to have a couple more during the holidays for you to do more revision on. And I'll give you a wee practice sheet out during the Easter holidays where you can practice some questions. We can catch up on the hangout. Hope you've enjoyed the show tonight then, and I'll see you in class, or I'll see you next week.